So let's talk about the correlation in a relationship between two quantities variables. So let's get started. In the previous lesson, we used scatter plots to evaluate the relationship between mileage and sales price for the ABC car. But what if we need to do more than observe the patterns in the data? What if we want to quantify the relationship between the variables? Correlation tells us two important things about the relationship between the variables. First, it can indicate whether a linear association between the variables exists. Second, and more importantly, correlation quantifies the strength of the linear association between the variables. The correlation coefficient, symbolized by R for the for sample data, quantifies the linear association between variables. The coefficient ranges from the -1 to +1. This value reflects the strength and direction of the relationship. The magnitude of the correlation indicates the strength of the association. A correlation near zero indicates a weak linear relationship between the variables. For a stronger relationship between variables, the correlation is closer to the +1 or -1. When there is a perfect linear relationship, all points fall on a straight line, and the correlation equals uh, either +1 or -1. The sign of the correlation indicates the direction of the relationship. If both variables tend to increase or decrease together, the coefficient is positive. If one variable tends to increase as the other decrease, so the coefficient is negative. An important characteristic of correlation coefficient is that it is not affected by the scale used on the axis when the data are plotted. To demonstrate, look at these plots. So, which plot show the stronger linear relationship between the two variables? The data in this graph seem to have a stronger relationship than the data in this graph, right? And yet, both have the same correlation coefficient. So how can be? So look more closely at the scale on the vertical axis. The values range from 60 to 78 on this graph, but the range from 50 to 100 on this plot. In fact, both graphs plot the same data. They only look different because the vertical axis scales are different because both graphs plot the same data. Their correlation coefficients are the same. For this reason, we may incorrectly interpret the relationship between variables if we rely solely on the scatter plot. Based on a high correlation coefficient, we might conclude that two variables uh, are linearly related. But how can we be sure this result is statistically significant? We use a hypothesis to determine whether a linear relationship between the variable exists. For correlation, the null hypothesis is that the population correlation coefficient represented by the Greek letter rho equals 0. No linear relationship between variables exists. The alternative hypothesis is that the correlation coefficient, the correlation between the variables does not equal 0. The linear relationship between the variables does not exist. For the data collected at ABC, the null hypothesis states that the correlation between mileage and sales price equals 0. The alternative hypothesis states that the correlation between mileage and sales does not equal 0. Before we test the hypothesis, we must first determine the significance level, or alpha, approximately for our situation. The most common significance level is 0.05, which indicates that we are willing to accept a 5% chance that we are wrong if we conclude that the correlation does not equal 0. To test the hypothesis, we use the p-value associated with the correlation coefficient. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. Here is the output from Minitab for the correlation between mileage and sales price. The p-value is less than 0.05. So should we reject or fail to reject the null hypothesis that the correlation coefficient equals 0? Because the p-value is less than alpha, so we reject the null hypothesis and conclude that the correlation between mileage and sales price does not equal 0. Based on the results of the hypothesis test, there is a statistical significant relationship between mileage and sales price. With that knowledge in hand, we can interpret the correlation coefficient. The correlation between mileage and sales price is minus 0.892. So what can we conclude from this correlation? First, we can conclude that this is a negative, meaning that as the mileage of a car increase, the sales price decrease. So it is a strong relationship. Okay, so determining how strong the correlation is between variables depends on the application. Okay, so remember, determining how strong the correlation is between variables depends on the application. For the sale of previously car, many factors beyond the mileage influence the final sales prices, including condition of the car, the color of the exterior, and local gas prices. But finding one variable with a correlation as high as 0.892 indicates a relatively strong relationship. In some applications, 0.892 may be considered a weak correlation. Think about a laboratory measuring radiation levels. It's important that the new Geiger counter be calibrated to a standard precisely and accurately measure radiation. Here, the technicians are hoping for a correlation of at least 0.998 and would consider anything less to be too weak to certify the new equipment. Keep in mind the following points when evaluating the correlation coefficient. First, correlation only measures linear relationships. Although other important nonlinear relationships may exist, we cannot use correlation to investigate them. We can determine whether our data are nonlinear by plotting them in a scatter plot. Another important point to remember is that the correlation coefficient is sensitive to extreme values or outliers. To illustrate, look at this scatter plot. The correlation coefficient is 0.785. Now, what happens when the outlier is removed from the data? The correlation increases to 0.832. That one point had a large influence on the relationship. So when we spot unusual values in our scatter plot, we should always evaluate the points to determine their cause. Often we can learn valuable information about our process based on these extreme values. Finally, if a strong correlation exists between the variables, it does not imply that one variable causes changes in the other variable. For example, a company that evaluates the relationship between average pay and the number of defects across its plants. They find a negative relationship between these variables. That is, the higher the average pay, the fewer the number of defects. The higher the average pay, the fewer the number of defects. But the company cannot necessarily say that the higher pay rate caused by fewer defects, right? Perhaps the plants with higher pay have employees with more experience who make fewer mistakes. In this case, more experience, not higher pay, may be related to fewer defects, or maybe plants with fewer defects reward their employees for good performance. The number of defects affected by the pay, not the other way around. To determine causation, we can conclude a design experiment. So let's talk about this design of experiments in the chapter 8 or chapter 9. So let's review. The correlation coefficient quantifies the relationship between two numeric variables. The correlation coefficient ranges from -1 to +1. Stronger linear relationships are closer to -1 or +1, whereas weaker relationships are closer to 0. The sign, the sign of the correlation coefficient indicates the direction of the relationship. Significant correlation does not imply a cause and effect relationship. Thank you for your listening. In the next lesson, we'll take a quiz